Over the weekends and change before spring break, we introduced two new types of functions, exponential functions and marginal functions. Exponential functions are functions that model anything that grows faster when there's more of it. Things whose growth rates are proportional to the number of things there are. So that includes things like populations. If the population of bunnies is double what it used to be, then you expect twice as many baby bunnies to be produced. Assuming that issues like predators and winter don't kick in. If you have some material that's decaying radioactively, when you have more of it will decay. That's an exponential behavior, exponential decay instead of growth. And if you imagine like money in a bank, if you have twice as much money in an interest-bearing account, the amount of money you get back every time the interest is compounded will be twice as big as it would be otherwise. So those are the examples we're going to hit today. Those are all modeled by exponentials. So there's a reason to study exponentials. Well, if you want to study exponentials, you kind of just need logarithms, right? You have to solve an equation that involves an exponential. How will you do it? You'll take a log. So let's do that reasons. So let's start with population growth. So, so if you have a population growing in some environment without any limiting factors, so that's what I meant by like there's not any issue with predators or winter kicking in or rabbits being hit by cars and stuff. That population will be modeled well by an exponential function. And here's what I mean by that. If you start with some initial population, P0, population at time 0, then the population at any time t is given by P of t equals P sub 0 times e to the kt. And just comment about how to parse this. You resolve exponentials first and then multiplication, so the kt is only in the exponential of the e. Where that k is some unknown constant parameter that you need to use the model to figure out. So I think the best way to understand this is let's use this to model a particular thing. Units. So P of t and P0 are counted in populations, so that might be measured in individuals if you're like a population of rabbits. It might be in mass if you've got like 5 kilograms of honeybees. That's probably more relevant than knowing that that's like 50,000 honeybees or something. T is a measure of time. It might be in hours or seconds or years, depending on how slow or fast the population grows. So a thing to make note is that e to the kt, I don't know what e to the 1 second is. I know what e to the 1 is. So the thing in that exponent can't have a unit next to it. So that means that constant k needs to be a constant with a unit of 1 over a unit time to cancel the units of time next to t. So let's see this in action. Let's use this, and this subtlety will come up. So here's an example. You have a population of bacteria growing in a petri dish. You start with a sample of 0.2 milligrams. After 1 hour, you have 0.3 milligrams. How long will it take until you have 1 milligram? So let's just write down the model we're using. P equals P is 0, e to the k. So, in this sentence, what parameters are you just told already? Yeah.
So a time, the start point and end point, so that would give us the rate.
Yeah, it'll be a slightly roundabout way to get the constant k, which is the rate of growth. But let's start with the initial population. What's P0? 0.2. What are the units? 0.2 milligrams. At some time, we were also given the population. So after 1 hour, so at t equals 1 hour, you know what the population is. What's the population at? Yeah. Oh, yeah. Sorry. Thank you. Better? Excellent. So by reading this sentence, the setup, what's the population by reading that at time equals 1 hour? Yeah. 0.3 milligrams. So that means the population at time 1 hour is equal to 0.3 milligrams. All right. So let's use that. I know that at time 1 hour, the population is 0.3 milligrams. But I also have this model that I can use. This model says that the population at time 1 hour, so this will give me a value for time to plug in, will be P0, which is 0.2 milligrams, times E to the unknown constant K times 1 hour. And so this is, that constant K is like the growth rate. The bigger that K is, the faster the thing grows. So I guess we need to solve for that constant K. Is K the only unknown in that equation? Yeah. So ostensibly, maybe it's solvable. And maybe we can, I guess we can try to solve it by just undoing everything one at a time. So the equation we need to solve is 0.3 milligrams. I'm going to include all the units. Equals 0.2 milligrams times E to the K, I'll include the parentheses, times 1 hour. And maybe for emphasis, the K is in purple because it's the thing that I would like to find out. I would like to solve that for K. What seems like a good first step? Divide the 0.2, and maybe I'll even divide 0.2 milligrams to the other side. If you weren't including the units already, then you wouldn't see the milligrams anyway, and they're about to disappear. So it'll become, have I painted myself? Yeah, I have enough space to do this. 0.3 milligrams divided by 0.2 milligrams is equal to E to the unknown thing K times 1 hour. All right. And now those, before we move on and do the next step, does anything cancel? Yeah. 1 milligram divided by 1 milligram is just 1. No units anymore, which is good. E to a power doesn't have a unit next to it, so the unit should go away. Milligrams cancel. So 0.3 divided by 0.2 is equal to E to the K times 1 hour. And in fact, 0.3 divided by 0.2, does that simplify? I've got like a decimal divided by a decimal. Yeah.
3 over 3.
Same as 3 over 2 or 1.5, if you like better. In fact, let's write that. 3 over 2 or 1.5? 3 over 2? 1.5. I think the 1.5 is have it by a small margin, but you don't have to do what I do. Both of those are fine ways to write E to the K times 1 hour. All right. So 1.5 is equal to E to the K times 1 hour. So what can we do? What should we do next if we want to solve for K? Well, you look at the side that has the K on it, and you read off what happens to K on it. You start with K, you multiply it by 1 hour, then you raise it to the E. So let's undo that E boss. What undoes that? Yeah.
We're going to take the square root of 12
Root of K times 1 hour of both sides. Root is what you want there. What undoes exponential functions? Logarithm functions. So if it were like T to a power, then that would be the right thing to do. K to a power, that would be the right thing to do. But it's not. The unknown is in the power. So you need to use a log to undo it. And the base is E, so you should use log base E.
All right, so this becomes ln of 1.5 is equal to k times 1 hour.
All right, so what's K?
That just give you ln 1.5.
If you don't include any units, then sure. If you include the units, then it'll be ln of 1.5 per hour. And I included the units this time because I wanted to emphasize what the units will be on the constant k.
The units will be something having to do with a reciprocal unit of time. Which makes sense. That K is like the growth rate. So you have to be something per time. All right, cool. That seems pretty okay. Let's write down the model we have.
So this means that the function that models this population is P of t is equal to P0, which is 0.2 milligrams, times E to the K, which is ln of 1.5, 1 over an hour, times time.
And right, if you suppress all the units, then the milligram and the 1 over an hour will disappear. But then you'll have to remember that time has to be in hours. Which is fine, but that's not necessarily a problem. Right? It's something you'll have to remember. This way the formula tells you what it means. So let's actually address the question now. We wanted to know how long until the population is at 1 milligram. So what equation do we need to solve? Yeah. Yeah. We want to know
When is this, the formula that we now have for the population of bacteria, when is that equal to 1 milligram? So 0.2 milligrams times E to the ln of 1.5, 1 over an hour, times T.
And in a lot of applications, you wind up suppressing units, especially because are all of the units of mass consistent right now? Yeah. So the milligrams will cancel anyway, so there wouldn't be any problem in this example with just forgetting the milligrams. And if you just remember that T is in hours, you can drop the 1 over an hour. Does that look like something we can solve? Yeah, awesome. Let's do it. What's the first step? Well, maybe I'll see what people want. This is definitely something you know how to solve. Should I just shut up for a second and let you solve it, or should I talk through algebra? Should I just be quiet? Okay, should I keep talking? Okay, those who would prefer not keep talking can just solve it. See if the answer is agreed. Let's solve it. What's the first step? If you want to get T on its own, that means everything on the side with the T needs to be moved to the other side, but in like the opposite order of how you would do it from the inside out on the left-hand side. So it's the first thing you should undo. Yeah.
Can you divide the 0.2 milligrams to the other side?
Let's divide 0.2 milligrams to the other side.
So that will give me E to the ln of 1.5, 1 over an hour, times T equals 1 milligram divided by 0.2 milligrams. And let's simplify that left-hand side.
Right-hand side? Simplify the this-hand side. What's that equal to? Yeah, 5. Right, 0.2 is a fifth. So 1 over a fifth should be 2. Nice. So right-hand side is just 5.
Or I guess like the algorithmic way to see that would be like 1 divided by 0.2, well, that's the same as 10 divided by 2 is 5.
All right, so we have gotten rid of the 0.2. Now I see e to the log 1.5 times 1 over an hour times time is equal to 5. So what next? I guess what's the next thing that we should target to get rid of? The e. I see e to a power. What undoes it? Take the log both sides, and the e will go away. So, doing that, we'll wind up with just color code a little bit, the stuff inside of the exponent. So ln 1.5, 1 over an hour times t. Underline in pink just to hammer home, this is the same as that, is equal to 5. All right. What next? No. I made a mistake. What mistake did I make? Yeah. Right, you can't just erase the So now it looks like I see some stuff multiplied together and then all that multiplied by t. So I could just undo that by dividing. So I guess I should divide the log 1.5 to the other side and multiply the hours to the other side. Fair enough. All right. So t equals ln of 5 divided by ln 1.5 hours. Feel pretty okay? Nice. We probably want a decimal approximation, right? We want to know, like, how big is that approximately? I don't actually care that it's log 5 divided by log 1.5. I would care much more, is that like between 2 and 3 hours, between 8 and 9 hours? That I think is something that I care more about. So, what is that about? Yeah, say it loud. 3.96. And presumably that's just approximate. Yeah. So, after approximately 4 hours, I'll just round that off to 4 hours, the population will be at 1 milligram. Does that feel okay? So that's one thing you can do with this sort of model. You can figure out how long it will be before the population hits some amount. Here's something easier you can do. You can just straight up ask the model, what do you predict the population will be at some given time? Let's give this population 1 full day to grow. How much do we expect there to be? Well, how would we do that? So this is the same population of bacteria we're thinking about. Yeah.
Instead of the population, we're trying to use time. So instead of replacing DHE, replacing just T.
Yeah. Absolutely. So in this one, what do I want to plug in for T?
Do you want to do 1 day or 24 hours?
Well, those are the same, so it shouldn't really matter. But which form of that would be more convenient for the way we've written everything so far? 24 hours. The times so far have all been in hours. Right, so like this, that 1 over an hour, if we have 1 day divided by 1 hour, that's 24. 1 day is 24 hours. So, I guess depending on how pedantic you want to be, technically a day is off by some small fraction of a second from being exactly 24 hours, and that's why there's this occasional second that you hear about. But I don't think we care about that amount of precision in this problem. So after 24 hours, that means we have to plug in t equals 24 hours. Do we still know what P0 is? Yeah, it's the same population. Do we still know what K is? Yeah, it's the same population. That constant K depends on the thing that's growing in the environment. It doesn't depend on exactly when you look at it as constant. So let's do exactly that.
So we still know P0. So we want to know the population at time equals 24. So I want to ask, should I include the unit or suppress units? Folks for include the unit? Folks for suppress the units? All right. If you want to suppress the unit, then suppress the unit. You'll have to remember that what unit it's supposed to be at the end. Plug in t equals 24 hours. This will be 0.2 milligrams times e to the natural log of 1.5, 1 over 1 hour times 24 hours. And maybe I'll point one thing out before we even begin this computation.
If you divide by hour and then multiply by hour, those units cancel anyway. So the time anyway, that unit could have been suppressed. Since it was all in hours. If you plugged in days, you would want to be careful with your units. All right, so there's this thing. Does that look like something that, using a machine, we can now just directly compute? I think so. Let's do it. All right, so doing that, 0.2, since I'm using a machine now, I'll just have to remember that there's a milligrams there, times e raised to the ln of 1.5 times 24. I get about 3,400 milligrams. And let's write that down, and then we'll discuss. Does this agree with other people who plugged it in? Did I make any typos when plugging it into the calculator? Seem okay? All right. About 3,400 milligrams. Should we change units? I'll leave it the same unit. Okay. If we wanted to change that to grams, would it be easy? So, matter of personal preference, whether you change the unit there. There's an argument both ways. There's an argument that 3.4 is easier to visualize than 3,400. There's also the argument that if you go and change units from one thing to another, you can disguise the amount that the thing is grown by. Going from 0.2 milligrams to 3.4 grams doesn't seem so big. Going from 0.2 milligrams to 3,400 grams seems big. Cool. Folks feel pretty all right? Nice. So you can talk about population growth this way. So there was a comment written on there in ink that I kind of didn't mention at all. All of this was done base E. Do you think that it really matters what base you use?
Yes.
You could use any base you want. Here's the reason to use base E. And the reason is calculus. So calculus has much better properties if you want base E than if you want base 5 or something. Which is why, generally when you do these models, if you're not going to pick a base that's designed to make the problem easy, you'll use base E. You could have done this all base 10, and then instead of doing natural log, you do log base 10. That's the only difference. That be all right? So, let's see another example, very similar, in which we'll pick a base that's suited to the problem. So here's another way of thinking about population growth. You can use any base you want. So let's pick a base that's suited to the problem. So the population can be given by P of t equal to V to the t, where this time that base is the unknown triangle.
And these models are in fact interchangeable. So who remembers the change of base formula for exponential functions? No, it was a while ago. Many people remember the change of base formulas for logs. Yeah. Yeah. Where here, this base could be anything you want, as long as they're both the same base. There's a similar thing for exponentials. A to the t can be written in terms of any other base you want. So I'll use base e right now. E to the t times ln of a. So let's use exactly that. Let's rewrite this expression, p0 times b to the t, in base e. So the p0 stays the same. p0 is still p0. We need to change this b to the t to something with base e. So it's p0 times e to the what power? It'll be t times the natural log of the old base. T times natural log of b. And let's just remember, that constant isn't called lambda, the constant is called k. Let's just remember the formula on the previous page. P of t is equal to p0 e to the k t. So let's just compare what we see on both sides. I see a p0 on both sides. I see e to a power on both sides. I see something multiplied by t on both sides. So I think we can translate between. If we wanted this to be the same as that, then what should k be? Let's see. Not quite e. So this k is the thing that's multiplied by t. So what's multiplied by t on this side? The natural log of b. So we can translate between both of these by the rule that k is equal to the natural log of b. And the point here isn't necessarily to hammer home exactly what the translation is between these two models. The point is to reinforce that it doesn't matter which model you use, they both carry exactly the same information. So we'll use this model for a different problem, and we'll notice that sometimes this one feels a little bit easier to use than the other. So let's do exactly that. All right, so let's imagine that you have a population of rabbits you're studying. After 4 days, you start with 3. After 4 days, you have 8 rabbits. That seems like an unreasonably fast growth rate, but whatever. It's a made-up garbage problem anyway. So how many rabbits do you expect to see at day 10? So let's start by determining the constants. What's the initial population?
3 rabbits.
3 rabbits. After 3 days, there's a population of 8 rabbits. So I can use this model plugging in t equals 3. No, wait. After 4 days, you have 8 rabbits. The problem went through some revisions in which the precise numbers were changed, but it was not done consistently. T is 4, right? At 4 days, you have 8 rabbits. So at time equals 4, you have 8 rabbits. So 8 is equal to P0, 3, times B, the unknown base, raised to the 4, because t is 4. All right. So b is right now some unknown parameter that governs the rate of growth. Does that constant b look like something you could solve for easily enough? Yeah. In fact, I think I kind of just want you to tell me what b is. With the stipulation that I would prefer an exact value. What are we getting? If you want to build up confidence, you can compare with the people around you before you say something boldly. I know sometimes that can be very intimidating, and I never make any mistakes on the board. Or, alternately, let's talk through it. What seems like a good first step if you want to solve that for b? Divide that 3 to the other side. So 8 over 3, which we could get a decimal approximation for, but I think that would not be helpful, is equal to b to the power of 4. All right, and it looks like on the right-hand side, I take b and I raise it to the 4th power. What undoes raising something to the 4th power? Yeah. Taking the 4th root of both sides. And maybe I'll choose to write that as b equals 8 over 3 to the 1/4 power. That's the same thing as taking the 4th root. If you happen to prefer to want to say the 4th root of 8 over 3, that's fine too. But I think 8 over 3 raised to the power of 1 over 4 is something you can actually plug into a calculator. How many people did get a decimal approximation? What'd you get?
1.28.
1.28. And I'm putting that in parentheses because I don't think I'm going to use that later in the problem. I'll have that for now. All right, so now that we have the choice of b, we have all of the parameters in the problem. This model now says this population is modeled. If you measure time in hours and population in individuals, population at any time will be the initial population, 3, times b, a thing that I know, 8 over 3 to the 1 over 4, raised to the power t. And maybe I'll just ask this really quick. Did that b seem easier to solve for than k was on the previous page?
Yeah.
Yeah. I mean, technically I don't think it really was, but you got to take a 4th root instead of taking a natural log, which maybe feels easier anyway. Anyway, so now that we have the model, let's use it to resolve the problem. So, what is it that this problem is actually asking about? How many do you expect to have at day 10? So, how do you do that? Yeah. Same as you were going to say?
Yeah.
Awesome.
Times.
Yep. We are given the amount of time, so we'll plug that in for t because t is time, and we just want to know how many rabbits. The model just spits that out. We don't need to solve or anything. So, let's do that. We want to know the population at time equals 10. Maybe we should do a quick unit check. Are all the units of time consistent in this problem? Is everything in days?
Yep.
Okay, cool. So there's no need to convert units. So that's equal to 3 times 8 over 3 to the 1 over 4 raised to the 10th power
And we could just straight up plug this into a calculator. There's some simplification to be done. But let's start with this, just decimal approximation. What is that?
Zero one nine. Cool. I'll round that to 02.
In fact, well, maybe first I'll ask this. There's lots of space to make mistakes when entering this into a calculator. So I want everyone who's using a calculator to get a chance to either confirm or question whether that is correct. I didn't compute it on my own. That seems not totally unreasonable. Actually, it seems a little high. What other values do we see?
Cool. Well, let's resolve that question. I think the answer is lots of parentheses. So let's do that. Because, right, we want to have the correct order of operations. So if you just do 8 over 3 raised to 1 over 4, as in, if you just do that, the way the calculator will read that is first exponentiation is resolved. So first it will resolve that. Which isn't what you want, right? So, like, that's where the subtlety is.
I would like to change my answer.
Is it to 35-ish?
Yeah.
Awesome. So let's enter it right up here with all of the parentheses. So the 3 multiplied is done last. Parentheses, parentheses. So 8 over 3 is all of the stuff that is in the base of this exponent raised to the power 1 over 4. Close parentheses again. And then I need to raise that to the 10th power. Well, I guess the 10 doesn't need to be in parentheses because it's just a single number. I'm in that habit because of the formatting tool that I use. If I say upper caret 10, it will think only the 1 is in the exponent and then the 0 will be on the bottom. You don't need to know that. I think I get the same as what you all know. So the way to resolve this is lots of parentheses. And this is one of the occasions where one of the things that Wolfram Alpha does is like kind of nice. Yeah, okay, so there's something that's not quite right. So notice Wolfram Alpha gives you this pretty quick version of what is typed. Is that the thing that I actually wanted? No. No. 10 is in the wrong exponent. Cool. Now it seems more like what I want. And Wolfram Alpha is even doing this thing where it says, oh, you're raising it to the 1/4 power. That means you want to take the 4. Fine. Cool. Folks feel pretty good. Let's point out, I guess, one simplification first. Does that look like an exponential raised to an exponent? What is an exponential raised to an exponent? What does that do? What's the exponential law we have for that? Yeah.
We multiply that first exponent by itself a certain amount of times.
We just multiply those two together. All right, like 2 to the 3 to the 5 is, yeah, you multiply these two powers. So this will be 3 times 8 over 3 to the 10 over 4, or if you like, 3 times 8 over 3 to the 2 over 5, or 2.5, I guess, if you prefer. Does that now look like something that's a little bit easier to just plug into a calculator? Yeah. So this is an argument for simplifying, right? If you simplify, you can save yourself effort in a stage which is usually easy, which is just plugging into a machine. Nice. 44.8 rabbits. Yeah, so let's address this notice at the bottom. Does it make sense for there to be 44.8 rabbits? No. So here's the way to interpret this fact. Whenever you make a population prediction using an exponential model, there's some weirdness with regard to non-integer values. And you can interpret this subtly as being this way. Like this population of rabbits is probably not reproducing every hour on the nose, every day on the nose. So of course you're not going to make an exact prediction ever. The rabbits might, give walk a little bit later this time. You expect the number of rabbits you have to be around 44.8 rabbits. So I guess approximately 45 individuals is what you would expect to see if you checked after exactly 1 day. But you would never. You wouldn't be surprised if it were off by 1. That feel all right? Nice. So the last model I'd like to use today, or something that grows exponentially, is interest rates. Yeah, which is something that's like pleasantly high if you have money to put into them right now. So here's the setup. You have $5 in a bank account, probably below the minimum balance required, but whatever. This is a made-up example anyway. And this bank advertises an interest rate of 5%, which percent literally comes from the Latin for 100. So whenever someone says percent, they just mean divide by 100. So that could be thought of as an interest rate of 0.05, compounded once per year. So what does that mean? That means at the end of the year, the bank is going to take the money you have, multiply that by 0.05, and then add that to your balance. And whatever stuff the bank is doing behind the scenes to make more money appear, whatever the bank is doing, but this is what they promise. So let's see what that means. So after 1 year, you'll have the original $5, so $5 times 1, plus an extra 5% of $5. So that's 5 multiplied by 1.05, also known as, I don't want to do it myself just because I saw some people plugging things into their calculators already. Okay. I guess I have to do lots of calculatory stuff on this page anyway. 5 multiplied by 1.05, 5 1/4. Money sign 5.25. The dollar sign is supposed to go before the dollar amount, right? Not after?
Yes.
Okay. Nice. So, let's suppose instead you want to leave that in there for 2 years. So here's the way the bank will interpret that. The bank will say, okay, I've just compounded this interest, and I'll just reinvest the same amount of money into the same account with the same interest rate. So that means at the end of that next year, they'll multiply by 1.05 again. Oh, well, multiplying by 1.05 twice, that's just what squaring does. Fine. So, if you want to put it in for 2 years, you'll have $5 times 1.05 squared. Oh, notice, you got slightly more than a quarter back on the second year around. You got 26.25 cents back. All right. What if you leave it in for 10 years? Then what would you do? Yeah, say it louder though. Yeah, you'll raise it to the 10th power instead. You'll multiply by this number 10 times. Five times 1.05 raised to the 10th power, about 8.1445. Oh, dollar sign goes at the beginning. It always seems wrong because you say dollars at the end. Right? Nice. So, there's no surprises there, that's just interest rates. A place where interpretation of numbers becomes slightly more subtle is not all accounts are compounded annually. They'll advertise an annual interest rate, but then they'll tell you it's compounded quarterly. So what does the bank mean when they say that? So let's suppose that instead you take that same $5, you put it in an account with an annual interest rate of 5%, the same annual interest rate, but this time it's compounded quarterly, also known as once every 3 months. I guess that's approximate 2. Months aren't the same length. Anyway, so that means each quarter, you'll multiply the amount in the account by 1/4 of 5%. So the bank will act like the interest rate is 1/4 of what it is, but it will apply it 4 times instead of 1 time. And just in order to see, well, I mean, let's see what people's intuition will be. Do you think this will be bigger than or less than the annual compounding? Bigger than? Less than? No intuition. All right, well, I feel like more people should have put their hands up for one of the 3 options. Anyway, let's see. So instead you take that same $5, you put it in with a 5% interest rate. So that means each quarter you'll multiply by 1 plus 5% over 4, which if you compute it out is 1.0125. So after 1 year you'll multiply by 1.0125 4 times. That's the same thing as multiplying by the thing to the 4th power. So let's do this. So I want to compute that. I'm going to take 5 and multiply it by 1 plus 0.05 divided by 4. And I want to raise that to the 4th power, giving me a total of $5.25, and I guess 47/100ths of a cent. Neato. And I guess depending on whether you follow the model outlined in Superman 3/Office Space, the bank maybe rounds that off to the nearest penny, or maybe it saves it, or maybe not. I've never actually seen the Superman movie, but I've heard it described in Office Space. That's the only thing I know about any of the Superman movies. Cool. All right. So if you wait 2 years, you'll multiply by it 8 times, and so on. In general, I'm running a little bit low on time. So if you have some initial principal, P, that's the $5 before, in some account with annual interest rate R, compounded n times per year, the amount in the account after T years is given by this model. The principal multiplied by something, that seems reasonable enough. It's something growing exponentially, so it should be multiplied by the principal. Well, if the interest rate is R compounded n times, the bank is going to say, I'm going to apply that interest rate, but only 1/n there. But I'm going to apply it n times every year. So there's now a formula that generates this. And here, I think, is the one last formula to hit, which we'll do some of the details to build at the beginning of next time. Sometimes you'll see advertised a continuously compounding interest rate. This continuously compounding interest rate will be given by taking the initial interest rate, the initial investment, the principal, P, multiplying by the natural exponential P raised to the RT. And you might think to yourself, what the heck is Euler's number E doing there? And this is actually where Euler's number comes from. If you take the formula above and apply it 1,000 times per year, 10,000 times, 1,000,000 times, what you'll wind up getting really, really close to is just this. So if you take an annual interest rate but compound it infinity times per year, this is where you'll wind up settling. And the thing more checking is go through these details, apply these formulas, and see if they give very similar answers. Cool. And if there's demand, we'll do that at the end of next time before we start in on trigonometry.
which is where we will be for the remainder of the semester.
I'm so happy I think I can. Nah, I'm probably just doing this every. It's usually what I do. I'm not put up and watching.
Yes and no. So you don't want to use your credit at all. You'll come up to my office and and I want to take your notes.
Oh, yeah, that's right.
The only thing that I'll sign it is not and the deadline for any of the extra credit is the end of the semester. Yeah. Which extra credit are you doing? Okay, but which, have you looked at any particular extra credits? Because there are a lot of them.
I'm looking for the, left.
Okay, I don't need to know the answer to that question. That's fair. That's fair. It does that. See you.
How was your spring break?
Restful. It was nice. I did a little bit of grading and thought about how nice it would be to have like some extra cost material left while when spring break was over, but I didn't actually do that. So I have a fair amount of work to do today and tomorrow, but I hope you all had a reasonably restful spring break.
That's your break.
Not bad. Ooh, I did notice that some people took advantage of this time to catch back up with some of the web walk or open-endeds. So in the course of doing that, if people had any questions that I guess came from any topic in the semester up till now that they'd like to ask about, now's a great time.